we want to think about what our results tell us about propagation of errors. You perhaps know that there's a rule that when you multiply two quantities, their proportional or percent errors are going to add. Or if you divide two quantities, same thing. In any case, recall that our x value is 3.6 plus or minus 0.4. 0.4 is 1/9 of 3.6, and 1/9 is about 0.11 or 11%. So we have what amounts to an 11% uncertainty in our observation of our x value. Our y value is 30 plus or minus 2. 2 is 1/15 of 30. 1/15 is actually 6 2/3%. I wrote this as 6.6%. It's really 6.6 repeating. I do have a few little dots down there just to protect myself, but should have written this as 7%, but I wrote it as 6.6, so we'll live with it for now. The acceleration, remember, was 2y over x squared, the quantity we were trying to find, and of course that was our f of xy function, resulting in the conclusion that the acceleration is 4.6 plus or minus 0.9. Now 0.9 is about 1/5 of 4.6, 9 is 1/5 of 45. It gives us about a 20% uncertainty in the value of a, and it's actually a little less than 20%. Now that's not going to work out particularly well here because I believe I've probably made some errors in mental arithmetic. Again, you can go back and double check and think about what these things mean and where my errors occurred, but it was probably just in the arithmetic. Now recall that delta f is fx delta x plus fy delta y. And we want to algebraically work out what the delta f ought to be in terms of the uncertainties in x and y. What's the uncertainty in f? And how's that related to the uncertainties in x and y in general? So fx, recall, was negative 4y over x cubed. Fy is 2 over x squared, so that our delta f is this expression. If we want to know the percent uncertainty, what did we do here? We divided our uncertainty by the value of the function. So we're going to do the same thing here. We're going to divide our uncertainty in f by the value of f. Putting absolute value signs around this because we don't care whether this is going up or down. We just want to know how much it can deviate, and we understand that it could deviate either way, either up or down. We don't even know if this calculation, delta f over f, is going to come out positive or negative, but whichever is the case, we're going to say the uncertainty is the positive of that value, or the absolute value of our result. Now for our specific example, we've said that delta f over f looks to be about 20%, the way our numbers came out for this particular set of values. Let's calculate delta f over f. Okay, delta f is just as it is here. F is 2y over x squared. That's our a, that's our f of x function. We used capital F before. We're using small f here, and I was a little inconsistent on that. Hopefully that won't cause too much trouble. If we divide this expression by this, well, we're going to multiply by the reciprocal of this expression, and it's easy to verify that what we get is what we see here. And I'm not going to take time to do the algebra and talk you through that. That's very straightforward. But the thing that we want to see about this is that we have a delta x over x and a delta y over y in this expression, so that the delta f over f expression can be rewritten as the magnitude of negative 2 delta x over x plus 1 times delta y over y. Now what do we mean by delta x over x? Well, that was our 0.4 over 3.6. That was our 0.11. So this delta x over x could be plus or minus 0.11. Delta y over y could be plus or minus 0.07, 2 divided by 30. And I, in this case, rounded that up to the 7% or the 0.07. To get the maximum possible value of delta F over F, we'll let our delta X over X be negative. So we'll assume a negative delta X, we'll assume the negative 0.4, very similar to what we did in our analysis. And we'll assume the positive 0.2 for the delta Y over Y. And we'll see that whatever X, delta X, and delta Y are here, this absolute value sign, this absolute value quantity cannot be larger than 2 times 0.11, which we'd get here with the negative delta X over X, plus the 0.07 we would get here with a positive delta Y over Y, telling us that our uncertainty appears to be 0.29, where my numbers came out with a 0.20. Now, I was doing mental arithmetic, but the arithmetic was not that difficult. Not sure where I went wrong, but I'm going to leave that in your hands. This shows us how the error propagates. It shows us that if we have an uncertainty in Y, that uncertainty contributes here. Whatever the uncertainty is in Y, that's going to be our contribution to the uncertainty in F. Now, we're dividing by X. Each time we divide by X, X contributes its 11% uncertainty. And the fact that we divided by X twice is revealed by the negative 2 here, or related to the negative 2. Dividing by X squared, we get a negative 2 here. You can think about why that's the case. But the 11% contributes once on the first division by X and once again on the second division by X, giving us a total error of 2 times the 11% plus the 7%, or the 29%.